My name is John Knapik. I work for Babcock and Wilcox Company. I'm part of the dry precipitator group out of Overland Park, Kansas. And I'm here today to talk about precipitators and power levels and just try to give you a basic understanding of how a precipitator works and how power, or how the total power in the precipitator can impact its overall collection efficiency. Precipitators are really rather simple. They consist of four parts: the precipitator itself, the transformer rectifier set, the automatic voltage controls, and current limiting reactors. A precipitator is a dust collector. Inside that dust collector, there are rows of parallel plates, grounded collecting plates. Those parallel plates form gas passages, so there's multiple gas passages across a precipitator. Centered in that gas passage are high voltage electrodes. So on the far right of the screen there, the flat plate is shown. That's where the dust is collected. And the high voltage electrode is the mechanism by which we charge the dust and we push the dust to the grounded collecting plate. The high voltage electrodes are driven by transformer rectifier sets. So they're called TR sets, transformer rectifier set. They produce the high voltage that's necessary in order to charge the dust particles and to propel the dust particles to the grounded collecting electrodes. On a precipitator, a small precipitator, it might only have, say, 3 transformer rectifier sets. On a big precipitator, like on a 800 megawatt utility boiler, they could have as many as 100 transformer rectifier sets. The transformer rectifier set is like a dumb device. It's driven by a brain. The brain is the automatic voltage control. Here's the automatic voltage control. So every transformer rectifier set will have an automatic voltage control. The brain actually sees what's happening in the precipitator through the return of the precipitator current called the milliamp signal. So the milliamp signal are the eyes to the automatic voltage control to see what's going on in its portion of the precipitator. Based on what it sees, then it controls the voltage going up to the transformer. So it sees and it says, my job is to constantly push to increase the power to the maximum to that transformer if possible. Well, if that's the case, why don't I just take the 480 volts in the power plant and send that directly to the transformer and let it be? It's because in precipitators, all precipitators, or most precipitators, have sparking going on in the precipitator. Sparking between the high voltage electrode and ground. Sparking in a precipitator is like a mini lightning bolt. In fact, if we have a precipitator in our test lab in Newport News, Virginia, and you literally hear the crack of the spark, and you smell the ozone that's created, and you hear the hiss of corona. So those are the parts, and since there's sparking going on in the precipitator, the control says, my job is to push that transformer to the max, but also I must look to see if there is sparking, and if there is sparking, I need to control it. So an automatic voltage control's job is 2 things: control the sparking in the precipitator and push the transformer to its maximum limits if there is no sparking. That transformer rectifier set is going to energize the high voltage electrodes in the precipitator. High voltage electrodes could take the shape of just a plain round wire, 1/10 of an inch in diameter. Or it might be a pipe with spikes looking like nails coming off of the spikes. Because of the fine radius of either the spike or the wire, they will generate corona once you get the high voltage high enough on the electrode. In general, it takes about 15 to 16,000 volts in order for the corona generation to start. Corona generation means one thing that you're doing at that voltage is you're actually creating light. Those plain, round, spring steel wires, if you had a darkened area and looked inside, would glow blue, just like this picture here. They're glowing blue because they're emitting photons, because they're at voltages that are getting things upset. Once you get to about 15,000 volts, and that transformer is capable of delivering up to 45,000 volts or more. But when you get to 15,000 volts, you'll generate corona. Corona, photons, do not collect dust, but also they will ionize the gas molecules, the flue gas molecules in the precipitator. It's the ionization of the gas molecules that contribute towards the charging of the dust particles and the collection of the dust particles. So photons just show that I'm at the stage where corona is being generated and I can start the precipitation process. A precipitator, basically, how much dust a precipitator will collect is based primarily on two things. One, the size of the precipitator. That makes common sense. The bigger the precipitator, the more dust or the higher collection efficiency it'll have. The second thing that affects the performance or the collection efficiency is the power, the total power, that the total useful power that the precipitator consumes. I say useful because there could be arcing that's not useful. There could be a thing called back corona, which is not useful. I don't know if I'll have time to get into those things. My presentation here is to concentrate on precipitators and power and to help you so that you understand it better. This is an early graph from a guy by the name of Herb Hall showing the relationship between collection efficiency on the y-axis and total corona power measured in units of watts per 1,000 ACFM into the precipitator. You could see that in the 100 to 200 watts per ACFM, just a little bit of power produces dramatic improvements in efficiencies. Once you get into the latter range there, more power increases efficiency, but not at the rate as in the initial part of the curve. Here's a chart from a coal-fired power plant, and it's showing you three things. The unit load, or the boiler load, in megawatts, so that's blue. You could see they're coming on in the morning, they're at low load, and they're ramping up to high load. You could see the opacity, which is the orange here. So low opacity at night and opacity increases during the day. And the third is the precipitator power. And in this case, and this isn't all cases, but in this case, when they brought the unit up to load, the precipitator power dropped and the opacity increased. This happened in this instance because the dust was highly resistive. And because of the temperature change in the precipitator that occurred from low load to high load, the high resistivity of the dust was aggravated. So high resistivity dust usually reduces the power in a precipitator. High resistivity dust to a precipitator is bad dust. Conductive dust to a precipitator is good dust. This same power plant, if they were burning a coal that produced an ash that was extremely conductive, when they ramped load from low to high, that power would stay at the same level. So the power wouldn't drop, it would stay at the same level. So resistivity of the ash collected in the precipitator affects the total power in the precipitator. And I'll try and explain that a little bit more later. As I said, the voltage control is the brains of the system. Each transformer has a voltage control. It looks to see if there's sparking. If it's sparking, control it. If there's no sparking, push the transformer to full tilt boogie. The next thing about precipitators, though, I think is important to you if you're going to attempt to understand them, is the amount of dust that's collected in each field of the precipitator. Let me try and explain that. This is a simple example where I have a precipitator with only 3 transformer rectifier sets on it. This precipitator, the gas flow would be from left to right. These are the grounded collecting plates. This is the hopper under each field. These bar graphs here represent the power levels on each of the 3 transformers. So this is transformer 1, this is transformer 2, and this is transformer number 3. The power levels, or the meters that I elected to show on this graph, are not power, but they're kilovolts and milliamps. Kilovolts are the voltage flowing into the precipitator. Milliamps is the current flowing into the precipitator. And the third one is the spark rate. If you're talking power, power is the product of kilovolts times milliamps, and it would be kilowatts. What I want to do is I'll just throw a number at the precipitator. Let's say 100 pounds of dust into the precipitator. Notice for this example that I've assigned collection efficiencies for each field of the precipitator. The inlet field has an efficiency of 80%, the second field 70%, and the third field 60%. In general, that's how precipitators work. The greatest efficiency is the inlet, the lowest efficiency is the outlet. Does anyone have any idea why? Why would it be easier to collect dust at the inlet to the precipitator as compared to the outlet? Yes, sir?
2 reasons. You slow the gas stream way down, so a lot of it falls out. Second reason is you've got a different particle size distribution at the inlet compared to the outlet. It's easier to charge and collect the dust.
Very good. Exact answer. If you examine the dust collected in the inlet hopper there, it's mostly the large particles, because fine particles need a longer time to achieve the charge to remove them from the gas stream. So the fine particles are mainly caught in the outlet field. So if I start with 100 pounds of dust, I also want to show what happens to the power levels, or the milliamps and the kilovolts and the sparking, as you go through a precipitator. In this case, this precipitator is collecting a conductive dust. If the inlet field has an efficiency of 80%, then the first field would catch 80 pounds of that dust, leaving 20 pounds to go on to the second field. If it has an efficiency of 70%, then 70% of 20 would be 14 pounds captured by the second field. In total now, I've removed 94 pounds of dust out of the gas stream, and I've got 6 pounds of dust going, real fine dust, going to that outlet field. And at 60% collection efficiency, then I would collect about 4 pounds of dust in the outlet field. Unlike a bag house, this is how a precipitator works. This is how all precipitator works. This is how you want the precipitator to work. I could adjust the power levels where I could get a more uniform amount of dust in each field, but the overall collection efficiency would not be as great as if I let the precipitator act in its normal way. And the most confusing thing to non-precipitator people, and even to some precipitator people, is understanding the power levels. In the inlet field, it collects most of the dust, and it'll have the lowest power. The outlet field collects very little dust, and it has the highest power. So when you look at a precipitator individually on a field-by-field basis, it could be confusing. I'm hoping to take a little bit of that confusion out of it. If you look at a precipitator and look for a barometer, look at total power, and then I think total power, adding all the transformers together, you won't get confused. But let's talk a little bit about why precipitator, the lowest power in the inlet and the highest power in the outlet. The reason for that has to do with the concentration of the dust in the gas stream. It has nothing to do with the resistance or the resistivity of the dust. So when you see this effect in the precipitator, resistivity is not an issue here. It has to do with the concentration. There's so much dust in the inlet field to the precipitator. You have a high voltage electrode, you have a grounded electrode, and you have a cloud of billions of particles of dust between the high voltage and ground. That dust is getting charged rather rapidly. That dust cloud represents a negative cloud between the highly negative electrode and the positive plate. Because there's a negative between a negative and a positive, it takes more voltage, which is the red, to push the current through. And current is measured by electrons that make it through the circuit, by gas ions that make it through the circuit, and by charged dust particles. And mainly in the inlet field, the fast movers, the electrons and negative gas ions, don't get into the circuit to be measured by the milliamp meter. It's mainly the charge from the dust that the milliamp meter is seeing. And that's why in a precipitator, because of the mobility of the charge carriers, current is low in the inlet, and opposite, once you get that cloud of dust away, the power levels will be high in the outlet of the precipitator. So if there's one rule on precipitators, it's this, and you could expect it in any precipitator you review. Always expect the precipitator current to increase from inlet to outlet of the precipitator. No ifs, ands, or buts. Use this, or we use this, as a troubleshooting tool. Because if this is what the trend predicts, then if you go to that middle field and find it lower than the outlet, if you go to that middle field and find it lower than the inlet field, so if it's down here, you know you got a problem. And you know the problem is not the process. You know the problem is the precipitator. If the problem is the process, it's going to affect usually every field on the precipitator. If it's just individual fields here or there, it's usually something in the precipitator or in the automatic voltage control. So this would be a person troubleshooting a precipitator. He goes to the voltage control. The voltage control has meters on it, amps, volts, kilovolts, and milliamps. He looks at the meters, and the key for him is he needs to know the size of the transformer that each control is controlling. So if I put the transformer sizes in there, on this precipitator, they put the smaller transformers, 750 milliamp, that's its rating, 45 kilovolts in the inlet. So these two fields are that size transformer. And they put the big transformers in the outlet. Why? Because we know precipitators pull the most current in the outlet and the least in the inlet. And for transformers, you want to load them close to their full potential. You want to load them at about 70 to 75% or more of their potential to get them to work right. They'll work down at 10%, but not as well. They'll also precipitate sparking or induce sparking. So in this precipitator, you look at it and say a control is to control sparking or push it to a limit. So if this control is set to run at 120 amps, 400 volts, 750 milliamps, 45 kV, and 30 sparks per minute, is it doing its job? Control sparking or push to the limits? It's doing its job. Its job is, it says, I'm seeing sparking going on here. I better control that sparking. And in my controlling of that sparking, this is the power levels that were produced. It's not at the rating of the transformer, but it can't. If you went to the rating, you'd have spark rates, well, you probably wouldn't achieve it, but higher spark rates don't necessarily mean better collection efficiency. In general, spark rates between 30 and 60 sparks per minute are ideal for a precipitator. 100, 200 in most cases are short circuit current and do not contribute to the overall performance of the precipitator. The second field, is it doing its job? Yes, it's controlling sparking. The third field, it's a bigger transformer. Is it doing its job? Well, it's set to run at 30 sparks per minute and it's only running at 10. Is it doing its job? Why do you say yes? Very good. Who's my friend back there that's giving all the good answers? Where are you from?
From Diener, but I used to teach a 5-day ESP course.
Okay, excellent. Would you like to switch places here?
I'll take it if you do anything wrong.
Okay. In this case, it's programmed to run at 30 sparks per minute, and it's sparking in that field, but it's also pushing the power levels to get that sparking, and it's happened to run out of current. The transformer is rated for 240 amps, and it's running at 240 amps. It is doing its job. And then the outlet field, oftentimes when you have a conductive dust in a precipitator, the outlet field will not spark at all. And so almost always on those transformers, you look to see that they're running full tilt boogie. Now this is on conductive dust. The second rule is that you look for current to increase from inlet to outlet of the precipitator. So on this 4 transformer precipitator, this is the inlet, this is the outlet, gas would be flowing this way. It's 300 milliamps in the inlet, 500 in the second field, 1390 in the third field, 1450 in the fourth field. Is it doing its job? We said a precipitator current should increase from inlet to outlet of the precipitator. Yes. No, wait a second. I'll challenge my guy in the back there. Look at, it's going 890 milliamps from the second to the third field and only 60 milliamps from the third field to the fourth field. Is there perhaps a problem here? Very good. He's shaking his head no there, even though he's hiding behind the big guy in the green. And he's right. You know, don't complicate your lives. If you had to examine and review a precipitator, as long as the current increases from field to field to field, it's doing its job. You got too much else to worry about. If you have a problem, give me a call, please. Sparking usually decreases as you go through a precipitator, and voltage is tricky. Voltage per unit current decreases, but that's beyond the scope of what we're talking about today in that. Now, if I came to the precipitator the next day and I found it operating this way, well, immediately you could see that the second field is a problem. One, because you had 300 milliamps in the inlet and it's only 170 milliamps in the second field. Two, it's set for 30 sparks per minute, and that control is having trouble controlling the sparking in the precipitator. It says, man, I am fighting this battle, but I am not winning. You told me to do 30 sparks per minute. I got it almost under control, but I'm at 40 sparks per minute. So for a precipitator person, that's another indicator that there's a problem. And the problem here for you people to recognize is that this is with the precipitator, it's not with the process. What do I mean process? Well, if you change coal, that might have an impact on the performance of the precipitator. Changing coal, going to a low sulfur coal, a higher resistive ash, affects the precipitator, but affects the whole precipitator. Process affects the whole precipitator. This is an example of just one field of the precipitator. It could be the wrappers, which are cleaning devices on that field, are out. Could be the hoppers are overfilled in that field, or something, but it's a single field of the precipitator. I'll just put this here. The slides will be available. Correct me if I'm wrong. Okay, so it just, if you had to look at a precipitator and the fields, energized are different sizes. You can't just simply look milliamps, milliamps, milliamps. You have to take the size of the field, and the size of the field is the width of the collecting plate. So you just take the milliamp number from the field, divide it by the width, and that'll give you a value. I don't even know what units. But then when you do that division, then you could compare. So if I looked at this precipitator and just thought that current should increase from inlet to outlet, I would think that there are problems with the fourth field of the precipitator because it's going up and then down. But because the fields are different sizes, this is a 6-foot plate, and these are 9-foot plates, and then back to a 6-foot plate, I need to divide this number by the width of the field. That'll give me a division that'll come up with a number of 15. 99 divided by 9 is 11. Division 20 and 25. So now when you look at it, you could see current is going down and then up and then up. And the problem here is actually with the second field of the precipitator, because current should go up and it's going down and then it's going up. And it's not the outlet field. The milliamps are going down, but those milliamps are spread over a lesser area. So if you measured the current per square foot or the microamps per square foot, that would also be an indicator, but that's just a simple thing for looking at them. As I've said from the beginning, the resistivity of the dust has an impact on the total power that the precipitator will operate at. The higher the resistivity, the lower the precipitator power. So if you're using total power as the barometer for the performance of the precipitator, it will be impacted primarily by the resistivity of the dust. The resistivity of the dust is impacted by a number of factors, but primarily in a coal-fired power plant by the temperature of the flue gas. Lower temperature, better conductivity, or lower resistivity. That's why at low load, it had good power levels, as opposed to high load. When you went up about 60 degrees in temperature, the power levels dropped. The other thing that impacts the resistivity of the ash is the chemistry of the ash. Primarily, sulfur trioxide works in conjunction with the moisture in the flue gas to make a weak sulfuric acid that coats the surface of the ash that makes it conductive. If you burn coal with low sulfur in it, then you're probably producing a dust that's more resistive. Unless there's other things in the chemistry, such as sodium, and then sodium can play a role both in hot temperatures and in cold temperatures in enhancing the conductivity of the dust particles in the precipitator. So, as my colleague said, there's so much to discuss in such a short time. But I hope in this time that I've been presenting that this is beneficial to you in understanding a little bit about the relationship between precipitators and precipitator powers. Here's another power plant that I was at where in this case they kept the load, help me, is that, yeah, that's megawatts. So the load stayed the same, but the power dropped and the opacity increased. And that's because they injected a sorbent, lime, in order to enhance their mercury collection, which would be the next topic of conversation. So what happened? Power went down. Why did it go down? Because of lime. What did lime do? Lime increased the resistivity of the dust in the precipitator. What about other sorbents? In general, sodium compounds would keep the resistivity the same and might even enhance it a little bit. So you might not see this phenomenon there. So chemistry affects the resistivity of dust. The resistivity of the dust affects the total power in the precipitator. Each field operates differently, and voltage controls are the brain. They got two things to do: control the sparking and push the transformer to its limits. Are there any questions? The question was, what is in precipitators the relationship between the distance between the high voltage electrode and the grounded electrode? And does it have any impact on collecting different particle sizes? The answer is twofold. Number one, precipitators primarily for 50, 60 years all had 9-inch plate-to-plate spaces. So the gas passage was 9 inches wide. In the 1980s, we began to experiment with wider spacings, where the gas passage went to 11 inches, then 12 inches, and nowadays we'll go up to as far as 16 inches from plate to plate, or 8 inches from high voltage electrode to ground. The plate spacing has no impact whatsoever on particle size collection abilities. It is the length of time that that fine particle is in the precipitator. So it's the treatment time. The question was, what happens to volts, current, and spark rate when you have a clean grounded collecting plate and you have a dirty grounded collecting plate? If the dust is resistive, then the more dust you have on the plate, the lower the power levels for that field. That's why wrapping, that is in the precipitators, wrapping is how you clean the plates and the devices they use to clean the plates. So that's why with them, they might be doing various routines to get the maximum cleaning that they possibly can in the precipitator. You could only clean it to so much though. If the dust is in the resistance range of about 10 to the 11th to 10 to the 12th ohm centimeters, you can have problems, and it leads to a phenomenon called back corona, and that's problematic. And it's confusing because the power levels will go up, and that's tricky. The question was the definition between dry precipitators and wet precipitators. A wet precipitator has high voltage electrodes. They could be wires, they could be barbed wires, they could be star pointed wires, anything with a sharp point, so the electrodes are the same. It has grounded collecting surface. The grounded surface in them might be a pipe, and you might only have one electrode in each pipe, and then you have 1,000 pipes. And the gas flow in them a lot of times is vertical in flow in a wet precipitator, as opposed to a dry precipitator, it's horizontal in flow. Or you could have a flat plate wet precipitator. The other major difference is in those devices, you normally do not need a cleaning device. Because of the wet nature of what you're collecting, it runs down like a film along the electrode and drops to the bottom of the precipitator. So there's no vibrators, wrappers, or whatever. A wet precipitator, for instance, in the utility industry, could follow a scrubber, because a wet precipitator will collect not just dry dust, but a fume. And the fume would be sulfuric acid mist, SO3. So although a scrubber's not as good at collecting SO3 as it is, of course, collecting SO2. So if you've got to collect that SO3 that's remaining, a wet precipitator will collect a fume. The question was, what's the difference between a cold and a hot side precipitator? In a power plant, you have the boiler, and you come out of the boiler, and typically you would go into an air preheater to preheat the combustion air and send it to make the boiler more efficient. That air passes over an air preheater, and it's getting its heat from the boiler flue gas that's going out towards the stack. Well, after the air preheater, typically a precipitator is located, and that's called a cold side precipitator because it's on the cold side of the air preheater. It's at temperatures of about 280 to maybe 390 degrees Fahrenheit, after that heat has been absorbed for the combustion process. If I take that same precipitator, and now this is my air heater here, and I just put it over here, so it goes boiler, precipitator, air heater, other devices, then now it's seeing flue gas temperatures of 700 or 800 degrees Fahrenheit, and that's why it's called a hot side precipitator. They thought that would be better in dealing with resistivity, but what happens to them, if there's not enough sodium in the ash, they get into a sodium ion depletion problem that occurs in time, takes a couple weeks to happen, and then they have resistivity problems. So, and they're a tough device. Basically, the question was, could we do something to get 80% efficiency? And don't hold me to that number, I'm just giving you relative examples, but can we get 80% efficiency in our example out of every field of the precipitator? Basically, it has to do with treatment time. And in order to get that higher efficiency of the extremely fine particulate in the submicron particulate in the outlet field, you will have had to have charged it for quite a long time, 16, 17, 18 seconds or more by that time. So that would be the key to the thing, is the charging time and that. And I've never done the numbers to see if I get 80% in outlet field, but that would be my guess. Time is what's needed.
So
I can't do anything. I can't do anything with power. All the power in the world ain't going to do it. I need the time in order to do it. The question was, what do you need to do to increase the time to have the resonance time in order to increase the efficiency of the precipitator? One, you'd have to drop the load of whatever device, if it's a cement kiln or a paper mill or a power plant or whatever, they'd have to drop load. Dropping load would increase resonance time. Or two, when the precipitator was built, it had to have a big enough term called its SCA, its specific collecting area, in order to accomplish the task at hand. We are retrofitting precipitators and trying to make them work better. Those usually entail rebuilding them, getting the alignment perfect again, new electrodes. The electrodes design can help in some cases, and new types of power supplies on precipitators. Instead of a single-phase transformer, they're using three-phase or switch mode power supplies that present a more true DC, an unrippled DC, another extended conversation. But what I'm doing is I'm maximizing the power. I can get more efficiency out of them. Whether I get enough or not, that's the million-dollar question. The question was, do you see applications where they have a computer, a smart system, looking at opacity and looking at precipitator power, and based on if the opacity is low, they reduce the precipitator power? Yes, we see it if it's permitted, because on some big, precipitator efficiency is related to the size of the precipitator and the power. If you got a big guy, if you got a big precipitator and good dust, you can cut the power at least by 60%. And probably not have, maybe have a 1% impact on opacity. Opacity would drop, or would raise 1%. It all depends on the combination of the two, the size and the dust and that. So if it's permitted, it can be done. If it's done, you're really, the emissions are minuscule and you save a lot of power. Any other questions? I need to get off here. Thank you very much. And I apologize. I could really put on a good show if you would have let me sing and dance out there. Thank you very much.